Speaker is Ognian Trifonov from University of South Carolina, who will speak on lattice points. Please, go ahead.
Thank you. First, I want to thank the organizers for organizing this great conference with so many nice talks. This is joint work with my colleague Ralph Howard, the first part of it, and the second part is joint work with my PhD student Jack Dowd. So the story starts in about 50 years ago. Zygmunt published a paper on spherical summability of Fourier series in 2 dimensions. And he needed the following theorem that if you take an arc of length, say cube root of 2 times r to the 1/3 of a circle of radius r, you're not going to have more than 2 lattice points on this arc. And so he asked his colleagues, and originally Schinzel gave a proof, but then easier proof was provided by Pelczynski. So in Zygmunt's paper, this is actually a lemma, but anyway, so I labeled this a theorem. And because the proof is so simple and everything we do is based a little bit on that, so here is Pelczynski's proof. So take 3 points, say A, B, and C with lattice, with integer coordinates, lattice points which are on the circle of radius r. Denote by A, B, and C the lengths of the sides of this triangle and the area by S. So on one hand, you have a simple formula for the area of the triangle using the coordinates. Now, because all the entries in this 3 by 3 determinant are integers, the result is an integer. And also it's non-zero because the 3 points are on a circle, so they cannot be on the same straight line. So the area of the triangle is positive. So cannot be 0, it's at least half integer, so it's at least 1/2. On the other hand, by a formula attributed to Heron from Alexandria, we have that the area of a triangle is the product of the lengths of the sides over 4 times the radius of the circumscribed circle. So because this is at least 1/2, well, you easily get that the product of the length of the 3 sides is at least 2r. So let's say C is the largest side. So this is less than or equal C cubed. Take cube roots and you get immediately what you need and what Zygmunt needed. So the question is, okay, so that's great. So this has been extended by many people. For example, Ciurello, Cordova, and Granville. So the exact constant has been worked out. People considered what happens if we take 4 points on the circle. What can we say about the maximum distance? What if we take more points and so on? It has been generalized to certain special types of ellipses, circle centered at the origin and so on. So we decided to go in a little bit of different direction. What if we deform a little bit the circle? So perhaps the same bounds still hold true for more general curves. So the question is, can we generalize this to more general curves? And for that, we need a little bit of geometry, and that was provided by my colleague Ralph Howard, who is a geometer. So here he proved the following theorem, that if you take 2 closed convex curves, C2 curves, that intersect in 3 or more points, then there are 2 points, one on the first curve and one on the second curve, where the curvatures of the 2 curves are the same. So it can be that the curvature of one curve is always bigger or the curvature of the other curve is always less. And once we have that, and that took a while to prove, it's not so easy to prove, you get immediately the following corollary, that if you take a closed convex C2 curve with a radius of curvature that has lower bound r, then if you take 3 distinct lattice points on this curve, then basically what you can do is you draw a circle through the 3 points, then the radius of this circle is going to be at least r, then you can apply the previous argument from the previous slide and get immediately the same bound. So, yeah, so it works not only for circles, but basically for any closed convex curve for which you have a lower bound on the radius of curvature. Great. So what about arcs? So can we take, say, portion of a curve? Is this still true for a portion of a curve? And the answer is yes, under certain conditions. So so basically what we proved is that if you take a C2 convex curve again, but now doesn't need to be closed, but you want the total curvature to be no more than pi, then if it intersects a circle of radius r in 3 or more points, then there is a point on the curve that has curvature equal to 1 over r. So basically, the constant here, pi, is sharp. So it takes a while to get it for when this is equal to pi, and if it is bigger than pi, we have counterexamples. So took some work to figure out the exact constant there. So basically, the corollary is, again, you can run the same argument as before. So instead of working with a closed convex curve, you can work with a C2 convex curve that has total curvature satisfying is at most pi. So basically, if you take a half circle, the total curvature is pi. So you don't want the tangent line to change its angle by more than a pi. So basically, you get the same conclusion that we got before in the case when you have 3 lattice points now on this arc. And again, the conditions are you want the total curvature not to exceed pi, and you need a bound, lower bound, for the radius of curvature. Okay, so that's great. So can we do more than that? What about lattice points close to an arc? So let's put some settings. So delta is going to be measure of closeness. How close were we to the arc? And suppose now we have 3 points which are not necessarily on the curve, but close to the curve. So they're within delta of the curve. That means there exist points A1, B1, C1 on the curve, so that A is within delta of A1, B is within delta of B1, and C is within delta of C1. And suppose we want to run the similar arguments, show that these points cannot be very close to one another. The maximum, maybe 2 can be close, but the maximum distance is at least what we had before, something similar to what we had before. And the idea is because the points A1, if we can show something about the maximum distance between the points A1, B1, and C1, because delta is small, then we're going to get easily by the triangle inequality something about the maximal distance between A, B, and C. And we need 2 things. Well, a key element of our proofs was the area of the triangle A1, B1, C1. So, okay, so maybe because the points A, B, and C are close to A1, B1, C1, the area of the triangle triangle ABC is close to the area of the triangle A1, B1, C1, which is true. It's easy to do. And the second thing, which is not immediately obvious, is that, well, before, our lattice points were not on a straight line, so the area of the triangle was not 0. So here we need to force the points A, B, and C not to be on a straight line. So that imposes some condition on delta. So the points better be sufficiently close to the curve, otherwise they may be on a straight line. Okay, so these are the 2 things, that main obstacles that we need to deal with. So the first one is relatively easy. So denote by A, B, and C the lengths of the sides of the triangle ABC. So we have the following simple lemma. So the difference of the areas of triangle ABC and A1, B1, C1 is at most the perimeter of the triangle ABC times delta over 2 plus 3/2 delta squared over 2. Now, the first delta term is sharp. So you give me a triangle and let me move each vertex by about delta. I can ensure that I can increase the area of the triangle, but that much was big O of delta squared. 3/2, that is not sharp, depends on, well, on the shape of the triangle, basically. And the easiest way to obtain the above lemma is to move just one vertex at a time. So suppose I just move the vertex C1. I claim that the difference of the areas of the triangle ABC and ABC1, provided that I don't move the third vertex by more than delta, is at most C times delta over 2. And the proof is so simple that I'm going to sketch it. So basically, the area of triangle ABC is AB times the height, which is the distance from C to AB over 2. And similarly, the area of the second triangle is AB times the second height over 2, where H1 here is the height, again, the distance from C1 to the line AB. And because these 2 points, C and C1, are within delta, well, the distance cannot change by the triangle inequality, cannot change more than delta. The difference height is at most delta, and you can make it exactly delta if you move the point in the direction of the height. So this is pretty much sharp inequality in one direction if you want to increase it. Now, if the height is less than delta, you cannot decrease to more than 0. So if delta is sufficiently small, it's sharp in both directions. So you can both increase and decrease by C delta over 2 if delta is less than the height. And applying this 3 times is going to, moving one vertex at a time, is going to give you basically this estimate. And because the second time and the third time you apply this second lemma, the length of your size may have changed a little bit, so you pick up a little bit of delta squared term. Okay, so that is one ingredient. We were able also to deal with the condition of the points not being on a straight line. So here is what we get. So basically, we assume that C is a convex arc. Again, the total curvature is at most pi. And the radius, we have two-sided bounds on the radius of curvature. Then we have some condition on delta, actually 2 conditions. And if these 2 conditions hold true, then we have an estimate for the total number of lattice points within delta of the curve. So if delta is 0 and R1 is R, you basically get pretty much what you get in Schinzel's theorem. So that is the true generalization of that result. And throughout the paper, we have tried to keep control of the bounds of the constants. So many of the constants are optimal. We have given examples of those. Okay, so this is what we get. So then the question is, what about, can you extend this result to more general settings? So far we dealt with the standard lattice. What if your points are from some other lattice, general lattice? So here's the definition of general lattice in the plane. So suppose you have 3 vectors, V0, V1, V2 in the plane, with V1 and V2 linearly independent. Then the lattice generated by these 2 vectors, V1 and V2, with origin V0 is basically V0 plus integer multiple of V1 plus another integer multiple of V2. So you're going to get the standard lattice if V0 is the vector 0, 0, the vector V1 is 1, 0, and V2 is 0, 1. Okay, so here is an example of a lattice. So ME plus M pi plus say root 2, M zeta of 3 plus N zeta of 5 plus cube root of 3. So in contrast to many results about lattice points close to curves that require standard lattice, the coordinates to be integers or rationals with some bound on the denominator, we have no restrictions whatsoever on the nature of these coefficients of the basis vectors. So they can be anything, transcendental numbers even. So the key fact that we need is basically that the distance between 2 points of the lattice is bounded. So from below, so for the standard lattice, the distance between 2 distinct points is 1. And the area of a triangle with vertices, lattice points, which are not on a straight line, is bounded. For the standard lattice, that constant is a half. Well, here we have something similar, that for each lattice there exist positive constants dl and al, such that the distance between any 2 distinct points of the lattice is at least this minimal distance dl, and the area of any triangle with vertices 3 non-collinear points of the lattice is at least a sub l. So you can tell what it is actually. What is a sub l is basically the magnitude of the cross product of v1 v2 multiplied by 1/2. So that is a sub l. Anyway, so what can we say about lattice is, because our proof is very robust and basically just uses that the distance between 2 lattice points is at least dl and the area is at most al, we're able to prove the previous theorem for general lattices. So basically, same conditions on the curve, bounds for the radius of the curvature, total curvature at most pi. We have conditions on delta that needs to be modified to account for the general lattice conditions. Then the number of lattice points does not exceed this quantity. So again, the lattice points can be those points that are in this general lattice. So they don't have to have components which are integers or rationals. Can be, again, V1 and V2 can have components that can be any real numbers. So that is how far we got to generalizing Schinzel's results. So more general curves, then arcs, then not only on the curve, but close to the curve, and also we allow general lattice in the plane. What about the three-dimensional case? We started with the simplest case, helixes, with my PhD student Jack Dalton, because it's very easy to compute things there. Well, helixes are in a sense cousins of circles, so it's a natural place to start. So constant curvature and torsion. So we were able to show that if you have helix of positive curvature and positive torsion, if delta is sufficiently small, so you have some bound that depends both on torsion and curvature. And if you take 3 points within delta of this helix, then the maximal distance between the points is at least a term that is basically the curvature, the lower bound, the curvature to the -1/3, and then a term that depends on the torsion. So basically, if your curvature is 1/r in the case of the circle, then you're going to get r to the 1/3, which is the right order of magnitude, what you get in Schinzel's case. We do need a term that needs on the torsion, because if the torsion is very small, it's possible that your lattice, your helix is going to be wound very tightly. So you may have lattice points which are very close that you get after a full rotation, then another full rotation, and so on. So there is a big arc length between them, but the distance, the physical distance in the Euclidean space is not so big. So the next step is, what about general lattice? And we started working on that relatively recently, a couple of days ago, Mike. So the general lattice in three-dimensional space is basically defined in a similar way. So you have V0, which is the shift in 3 vectors V1, V2, V3 linear independent. Then the three-dimensional or general lattice is V0 plus integer multiple of V1 plus integer multiple of V2 plus integer multiple of V3. And a few days ago, my co-author Ralph Howard pointed out that the same thing that we have for two-dimensional lattice holds true for three-dimensional lattice as well. So if you take 2 distinct points from that lattice, there is a minimal distance between them. And if you take 3 points which are non-collinear from the lattice, there is a lower bound on the area of the triangle. So that will allow us to generalize that result on the previous slide. So this result here, for the case of general lattices, just we need to go through the proof. And everywhere we use, the minimal distance between 2 lattice points is 1, place DL, and everywhere where we use the minimal area is 1/2, replace that by A sub L. So it's going to be pretty straightforward. We didn't have time to do it, but there is no reason this will not work. It will definitely work. We're going to get this analog of this result for lattice points from a general lattice. And then the next step is, of course, well, what if we deform this helix a little bit? What if we squeeze it or stretch it a little bit? So basically, we would like to have the curvature between some bounds and the torsion between some bounds, and be able to say something similar. And we don't have that. We need a little bit of differential geometry ingredient for that, but having my colleague and co-author Ralph Howard help us, I'm pretty confident that we're going to get that in the near future. So that is where this is headed. But for now, we have it for helixes, and in a couple of days, helixes and general lattices. So that's pretty much it. Thanks.